So we were discussing about the applications of microcanonical ensemble formalism to study some common systems. So already we have seen how to analyze the classical ideal gas using microcanonical ensembles. As a second application or example of MCE, we will be taking the case of the one-dimensional simple harmonic oscillator. So consider a simple harmonic oscillator in one dimensions. Simple harmonic oscillator in one dimensions. Now, the most common example for such a system would be a spring mass system. The best example would be a spring mass system. Say one like this. You have got this one, a frictionless surface connected with the spring of spring constant K and a mass EM. Let's take this axis to be the x-axis. So once disturbed, the system will be executing SHM with let's say that the total energy of the system be E. So let E be the total energy of the one-dimensional simple harmonic oscillator, total energy. And you know that in the case of a simple harmonic oscillator, the total energy is fixed. Total energy is fixed because we usually take that there is no any damping. The total energy is taken to be fixed. Now, the classical Hamiltonian for the system would be, for a simple harmonic oscillator, the classical Hamiltonian, you can say that H, a function of Q and P, that would be simply the sum of the kinetic and potential energies because it's a conservative system. So I can say this is equal to P square by 2m plus half KQ square, where Q is the coordinate here it will be X, right? So we say that this is my equation number 1, where the common solution Q is equal to, I'm just discussing the solution, it's of no use to us in our present discussion. Q is equal to, say, let's assume either it will be a sine function or a cosine function. Let me take it as a cosine function. So A cos omega t plus phi, that's the usual, the coordinate or displacement in SHM. It can be a sine or a cosine. I'm taking a cosine for the time being. And so if this is the, if a cos function is taken as the displacement, then you know that the momentum P will be equal to mass times the generalized velocity, that is Q dot. So that will be equal to some minus em omega, then A cos will become, of course, sine minus sine. So that is the thing, omega t plus phi. So these are the Q's and P's, right? What is A here? A here is, of course, the amplitude. In all these equations, we use the same meanings. A is the amplitude, omega is the angular frequency, and this omega is equal to root of K by M. Recall all those facts. Okay. Now, you know that the total energy of the oscillator, the total energy. So just you can use equation number 1 itself actually, but for a completeness I am writing separately. Total energy of the oscillator, which we are taken to be E, which is a constant. Total energy of the oscillator, you know that E, right, that is equal to half KQ square plus what? P square by 2m, which you can substitute for Q and P you can substitute. So it will be equal to something like m omega square A square by 2 cos square omega t plus phi. I'm substituting for Q and P using this relation, okay, plus P square by 2m. So that will be again m square omega square A square, okay, sine square omega t plus phi divided by 2m. So you can just cancel away one of the m here. So finally what happens is that m omega square a square by 2 is common, so that is equal to half m omega square a square. So cos square plus sine square is equal to 1. So that is our expression. You know that m is a constant, omega angular frequency is also constant, a amplitude of oscillation in SHM, if there is no any damping, in SHM we neglect damping, so amplitude is a constant, so we can say that which is a constant. So this is already known to a known fact, we just have reproduced it, that's all. Okay, total energy of the harmonic oscillator is a constant, that's a fact. And since energy is a constant, you know that we can consider this system, the one-dimensional simple harmonic oscillator, a member of the microcanonical ensemble, because you know that for a microcanonical ensemble the macro state is described by E, V and En, right? The number of particles here n equal to 1, we are considering a simple case of one particle. We can later extend it to n particle harmonic oscillator system. Okay, see the energy here is what fixed. So since E is fixed, we can take that the system belongs to the microcanonical ensemble, right? Now you know that this is the energy. Okay, so this one is the energy, which can be rewritten as, so substituting for k from this equation, omega equal to root of k by m, so k will be equal to m omega square. Substituting k equal to m omega square in the energy expression, E is equal to, okay, so what it will become is it will become m omega square q square by 2, right, plus what, p square by 2m. You know what we are trying to do, which can be rewritten, so divided throughout by E, so it will be written as, so dividing by E and rearranging, 1 left side will be 1, so it will be equal to q square divided by 2E upon m omega square. I am taking m omega square from the numerator to the denominator, so that can be rearranged like this, plus what, p square divided by, so there will be an E coming in the denominator here, by 2me. So you know that this one is nothing but the equation of an ellipse. Okay, equation of an ellipse with q and p as the axis. So this exactly what we have seen in our classical mechanics discussion also, the phase space trajectory, right? Okay, so this is the conclusion. Therefore we see that we call it as equation number 2 or something like that. So the phase trajectory, okay, once again we conclude it. Okay, that's all. It's a repetition actually of a one-dimensional harmonic oscillator will be an ellipse, So just in the diagram on the slide, okay, several ellipses are shown here, concentric ellipses are shown here. We will discuss why several ellipses are shown. Just take one of the ellipses here. So we say that I am taking the inner ellipse here. So this is the case you are discussing now. Now that is the phase trajectory of the representative points. Okay, it's an ellipse, right? Now with the ellipse will be having a semi-major axis and a semi-minor axis. So let's say that the semi-major axis here, we can conclude here, the semi-major axis, let's call it as usually A, that will be equal to, see, x square by a square plus y square by b square equal to 1. That is a form of equation number 2. So what is the semi-major axis here? So we are taking see, q and p. So q is in the place of x, so whatever is in the denominator is what, a square. So a is equal to root of the denominator of q square, which is 2e divided by m omega square. That is a semi-major axis, and the semi-minor axis is of course root of 2me. Root of 2me will be the semi-minor axis, right? Therefore, can we calculate what will be the area of the ellipse? What will be the area of this ellipse? Therefore, area of the ellipse, all this discussion we have done in our classical mechanics classes. Okay, while we discuss phase space, area of the ellipse, okay, that is a, let me say that just I'm avoiding, you see, area of the ellipse, let's write it as such, that is equal to, what is the equation, that is we have remember from Kepler law and all the discussion we have seen, it is equal to pi AB, right? In the case of A equal to B, semi-major axis equal semi-minor axis, the ellipse will turn into a circle whose area will be pi r square. When A equal to B equal to R, that is known as a pi r square. The circle, so it is the area is pi AB. Okay, so pi AB. So I can just substitute for A and B. So pi into, what is A? A is equal to root of 2e by m omega square. That is what we have seen, that. Into B is what? Root of 2me. Root of 2me is the. Now you can just cancel away and make modification. So root 2 and root 2, that will be 2. So it will be equal to finally 2 pi. Okay, 2 pi. Then what will happen? M, here there is a root m and there is a root m in the numerator. So they will be getting cancelled. Okay, and there is an omega also, right? So 2 pi e into root e will be e. So that is 2 pi e divided by omega. That is the thing what you are going to get. Area of the ellipse will be equal to 2 pi e by omega. And you can see that 2 pi and omega are constants as far as any harmonic oscillator is concerned. See, so we can say that, of course, the energy of the harmonic oscillator depends on the initial disturbance that you are giving. If you extend the spring more by compressing or by giving more energy, then that will be the energy of the harmonic oscillator. So it depends on the disturbance. Okay, so we can say that the energy, therefore, the area of the ellipse is directly proportional to what? The energy. That is what you have to understand. The area of the ellipse is directly proportional to the energy. Hope you remember this discussion we already had done. Why? Hope you remember that if you are drawing multiple concentric ellipses, then see, the outer ellipses are having greater area. So we say that the outer ellipses usually correspond to what? Greater energy as well, right? So that is a thing that we have seen earlier. Okay, now as I told you, or as we have discussed earlier, having a fixed energy is only an idealization. Usually no system can ever have completely constant energy. There will be some variations in the energy that we have to practically permit. So if we allow the energy of the oscillator to vary, if we allow, as usual, that is what is happening in real system. The energy, if we allow the energy to vary, and we permit always some variation, okay, very small variation, vary between, what is the variation? We have been permitting a variation of delta, right, between. So what is the variation? So it will be supposed to vary between e minus delta by 2 and what? E plus delta by 2. Instead of e equal to a constant, we relax the condition for real systems and we permit there will be some what you can say that a small variation. Instead of sharp energies, we will be permitting a variation of energy delta. Okay, then what will happen? Instead of the representative points lying on the single trajectory having energy equal to E, we can say that the representative points will be now lying in an energy shell of thickness delta, of energy thickness delta, or what will be the area. Therefore we can say that if you allow this thing, the representative points, I am writing RP points, lie within, instead of on a single trajectory, on a single elliptical line, it will be lying within a shell, within a hypershell, within a hypershell. What will be the area of that hypershell? Of area, of course, area of the ellipse is 2 pi e by omega, okay, of area. So corresponding to energy E, the area is 2 pi e by omega. So what will be the area corresponding to delta, okay, energy, delta, the spread. So that will be of area 2 pi by omega into delta, 2 pi by omega into delta. So the representative points will be lying within a hypershell of area 2 pi by omega into delta. Okay, so this is our conclusion. Just remember this one, we need it later, right? Now so far we have been discussing the harmonic oscillator as a classical system. Now if we consider the quantum mechanical picture of harmonic oscillator, but quantum mechanically, the energy eigenvalues of a harmonic oscillator are quantized. Okay, the energy of a harmonic oscillator are quantized. They cannot have continuous values, right? So they are quantized. So the energy eigenvalues are given by En we are using the quantum picture also along with the classical picture. En corresponding to the quantum number En. En is equal to n plus half. Hope you remember these equations. You have used this in vibrational spectroscopy and many other places. En is equal to n plus half some h nu or h cross omega, you know. Okay, always remember that it is same as h nu is nothing but h cross omega, you know. So just divide by 2 pi, okay, and multiply by 2 pi. So it will be 2 pi into nu in the numerator. So 2 pi f is what? H by 2 pi is just what? H cross, and 2 pi into nu is 2 pi f, that is what? Omega. So either you can use h nu or you can use what? H cross omega. Both are same. H nu is equal to h cross omega. Only difference is that we are using angular frequency in place of what? The linear frequency. Hence the symbol h becomes what? H cut or h cross omega. So En equal to n plus half h cross omega, where you know the value of En's are 0, 1, 2, 3, etc. So this is our common idea, right? Now in the language of phase space, okay, if you use the quantum picture in the language of phase space, what we can say? We can say that in the language of phase space, the representative points of the system must be moving along any one of the trajectories. Okay, I repeat, in the language of phase space, therefore, that's the meaning. In the language of phase space, the representative points, if the energy is quantized, the representative points of the system cannot move. It cannot move along any trajectory. It can move only along those trajectories, okay, with the permitted value of n, right? So representative points of the system must, we are bringing an additional condition, must move along one of the trajectories, any one of the trajectories. It cannot move in along any trajectory, so it can move along one of the trajectories, okay, with n equal to 0. Either you can move with a trajectory n equal to 0, corresponding n equal to 0, you know, E0, the ground state energy will be equal to half h cross omega. Okay, that is what we call as the 0 point energy in the case of harmonic oscillator, right? N equal to 0, or it can move along another trajectory with n equal to 1. When n equal to 1, the energy will be 3 by 2 h cross omega. Okay, so when n equal to 2, the energy will be 5 by 2 h cross omega. Means all energies are not possible in the case of quantum systems. So n equal to 1, 2, 3, etc. It means that the trajectories of the representative points in the phase space also becomes what? Quantized, and what is shown in the figure on the screen here. So you can see that what is the meaning here. The meaning here is Q and P has been, the phase space trajectory has been drawn for various n values. So the innermost trajectory shown here, which I am now marking with a red arrow, that corresponds to, that is a minimum value of the energy possible, okay, corresponding to that elliptical path, there will be an energy, and that, what will be the energy corresponding to this track? The energy corresponding to this track will be, of course, what? H cross omega by 2, corresponding to n equal to 0. Equation number 3 gives E0, the 0 point energy is equal to h cross omega by 2. Okay, so that will be having energy is equal to E0 equal to h cross omega by 2. Now you can see that after E0, the next trajectory is, okay, having, it corresponds to n equal to 1. When n equal to 1, okay, the second phase space trajectory is possible, whose energy will be equal to, I can say E1 is equal to what is that? 3 by 2 h cross omega. Okay, 3 by 2 h cross omega. Now you can see that the third trajectory is shown here. This is the third trajectory, okay, whose energy will be equal to 5 by 2 h cross omega. So E3, you can say, or E2, actually to be E2 will be equal to 5 by 2 h cross omega, and corresponding to n equal to 3, you will be having another trajectory. All the trajectories, you know, that will be clockwise oriented. Okay, so that is corresponding to n equal to 3, E3, that will be equal to 7 by 2 h cross omega, etc. Right? So this is the thing that happens in the quantum picture. Right? Now, let me take, for example, let's consider what will be the area between two consecutive trajectories. the area between two consecutive trajectories. So already it is shaded for you here. So let us take, for example, consider the area between n equal to 1 and n equal to 2. So see, for example, I am just shading some area. Already it has been shaded dark in the diagram here. Suppose we are interested to know what is the area between two consecutive trajectories with an energy difference equal to delta. Let me say that let the energy difference here is equal to delta. The energy difference between these two trajectories will equal to delta. You know what is this delta? Delta will be equal to, of course, h cross omega, because you know each of the nearby trajectories are having difference 5 by 2 h cross omega minus what 3 by 2 h cross omega, or 7 by 2 h cross omega minus 5 by 2 h cross omega. Each of them are differing by an energy equal to h cross omega. So if, okay, so let me just continue with this one. Therefore the area between two consecutive trajectories. This is only a discussion so that we are familiar with what the use of ensemble formalism. That's all. Okay, no new information you are going to get here from the discussion. So area between two consecutive trajectories. Okay, see with energy difference. With energy difference delta, what is delta equal to? So delta will be equal to En plus 1 minus En, right? En plus 1 minus En, that will be the difference. So what is this? The difference will be equal to, of course, h cross omega. Is it right? So area between consecutive trajectories with energy difference delta, and delta is equal to h cross omega. What will be the area? That area will be equal to that area is equal to, you know, it is 2 pi by omega, you know, into delta. This is what we are seeing, 2 pi by omega into delta. Already we have just seen that one. That is a hyper shell of area, right, which is shaded here, 2 pi by. Now equal to delta, if you take delta equal to h cross omega, as we have taken delta equal to h cross omega, what will be the area equal to then? So it will be equal to, you can see, 2 pi by omega into h cross omega. So omega and omega will be getting cancelled over here, and that is 2 pi into h cross. H cross is h by 2 pi. So 2 pi and 2 pi will be once again getting cancelled. So that will be finally giving you what? H. See, the Planck's constant, right? So this is something a striking result, because you know, hope you remember, we had we had used this idea before. The minimum phase space volume, right? The minimum phase space volume for a single particle system, in one dimension will be h. In 3 dimension will be h cube. For n particle will be h raised to 3n. Hope you remember. So we are getting, since we are discussing a one-dimensional harmonic oscillator, single one-dimensional harmonic oscillator, we are getting that area between two consecutive trajectories, which is the minimum area, right? Because you know, you cannot have an area that is lesser than this one practically, right? So this minimum area is you are getting between the two consecutive trajectories, you are getting it as equal to h. And you know, in the case of one-dimensional harmonic oscillator, we call it as area. In the case of you say 3-dimensional or 2-dimensional harmonic oscillators, instead of area we have to call it as by the name volume. So area in one dimension is equivalent to volume in n dimensions. Okay, that means volume. Okay, so area has got the status of volume when you discuss about what the 2-dimensional phase space cases. So we are getting the same result. That was a striking result. Now we can further we can carry on the discussion. Suppose here we have taken delta equal to h cross omega. If in a general case, if or we can take it that consider say for arbitrary values of E and delta, means we do not insist that, we do not demand that delta equal to h cross omega. Let's take some arbitrary value of E and delta. Okay, that is delta not equal to h cross omega. We need not make that delta equal to h cross omega. Let's see if what happens. Okay, but only one condition, such that we can take some arbitrary values of E and delta such that the value of delta is very small. Okay, so E is very much greater than delta, but this delta is very much greater than the minimum value, that is h cross omega. Okay, so delta is lying between, delta is greater than h cross omega but less than what? The total energy. So if such a case, in such a case, what will be the number of eigenstates within delta? Therefore, number of eigenstates means energy states. Number of eigenstates in the language of quantum mechanics within this range of energy delta, within delta energy range. Okay, within delta range. So of course that will be equal to, let's call this one by some gamma, right? Number of eigenstates, you know, each eigenstate corresponds to a microstate. Okay, quantum mechanically, each eigenstate is an accessible microstate. Therefore, a number of eigenstate is same as what? Number of microstates, which we have been using as omega or gamma, whatever it is. So, you know, what will be the number of eigenstates within delta? Okay, the minimum energy is h cross omega, of course. So, delta, it will be equal to delta divided by h cross omega. It's quite simple because delta is the total energy given and h cross omega is the energy quanta. So, how many eigenstates will be there? It will be equal to delta by h cross omega. Okay, that is quite logical. Therefore, we are doing it in the reverse sense. That's all. Area or volume. Okay, you know, area here is equivalent to the volume of the phase space. Area of the phase space. Therefore, area of the phase space corresponding to, how much area will be there? Corresponding to one eigenstate. Corresponding to one eigenstate, how much area will be there? That's what we're going to calculate. So, this is number of eigenstates, gamma, right? So, then the area of the phase space correspond to one eigenstate. Let me call that one as some omega 0. Okay, area or volume, omega 0. Omega 0 will be equal to the total area, right? The area corresponding. So, that is equal to total area. What is the total area? Let me call that total area as some omega prime divided by gamma. So, total area is nothing but 2 pi delta, right? Correspond to delta. The area is what? 2 pi delta by omega, which already we have seen, divided by what is the number of eigenstates or number of eigenstates within this delta? That is delta gamma is already obtained here. Delta divided by h cross omega. So on simplifying, you know that the delta, all those things will cancelled. Delta and delta getting cancelled. Okay, and see this omega and omega also will be getting cancelled. Okay, and here it is what? 2 pi and h cross. So it is equal to 2 pi h cross. You know, h cross is h by 2 pi. So which you are again getting as what? H. You can see that. So what's the meaning? The meaning is that the volume, see that, just see, understand what we have obtained. So the volume of the phase space corresponding to one eigenstate. Quantum mechanically, as I have already mentioned, okay, one eigenstate represents one microstate. And that is what the minimum phase space volume that we have been seeing. We are getting it as quantum mechanically. Once again, okay, we are getting it is equal to h. So which gives, again gives the minimum phase space volume corresponding to or equivalent to one eigenstate. Thus, we can say that. So what we have taken is, once again remember, we have taken a one-dimensional harmonic oscillator. Single one-dimensional harmonic oscillator. So n is equal to 1. Capital N equal to 1. One-dimensional simple harmonic oscillator, n equal to 1. Therefore, we are getting the minimum phase space volume is equal to how much? Minimum phase space volume omega 0 we got, it's equal to what? H. So therefore, one three-dimensional harmonic oscillator, omega 0 will be equal to h into h into h. It will be equal to h cube. And for a system of n such a three-dimensional harmonic oscillator, like a system of molecules oscillating or crystal, you know, Einstein model and all, hope you remember that, solid state physics. So a system of n three-dimensional harmonic oscillators, we can say that the omega 0 will be, of course, we can just extend it. It will be equal to h raised to 3n. h raised to 3n. Okay, so that is the discussion that we have taken. So that's about see the concept of microcanonical ensemble applied to the case of a simple harmonic oscillator. Please go on reading the relevant part of the textbook and try to understand better. So that was about quantum harmonic oscillator. And I think the present module can be completed with a simple discussion of what is known as density of states. So I will be discussing about a very important concept in statistical and solid state physics, okay, known as what the density of states, which will be helping us to do the next topic of canonical ensembles, next module. So please go on reading the relevant part of the textbook and any reference material, all the PDF notes that is given to you, so that you are updated. Okay, thank you.